You ever stop and think about how an online bank transfer just happens? Or how cloud services seem to work flawlessly all the time without ever falling apart? Well, behind the scenes, there's this kind of invisible magic at play. It's called consensus, and it's this secret agreement between computers that basically powers our entire digital lives. So, how in the world does it actually work?
See, this is the core of the problem, right? We don't have one giant supercomputer running the show. We have thousands, millions of different machines. We call them nodes, and they all have to work together. So what happens when they have conflicting information, or one of them just fails? How do they all get on the same page to make a decision?
Let's break it down with something simple. Ice cream. Imagine 3 computers trying to decide on a flavor. 2 of them vote for chocolate, 1 votes for vanilla. Pretty simple, the majority wins. But here's the really important part. That one computer that wanted vanilla, it has to accept the group's decision. It has to agree that the official flavor is now chocolate. Everybody ends up in the exact same state.
Okay, so that ice cream vote is a nice, simple way to think about it. But in computer science, this whole process of agreeing on something has some very, very strict rules. So let's dive into what consensus formally means.
So at its heart, consensus is basically a protocol. It's a set of rules that lets a whole group of computers agree on one single thing. And the whole point of this is to build an incredibly reliable system. The system has to keep working, even if some of the computers involved suddenly crash or go offline.
Right, so for a consensus system to be truly trustworthy, it has to follow 3 non-negotiable rules. First up is agreement. This one's simple. Every single computer, every node, has to land on the exact same answer. No confusion, no exceptions. Then there's validity. This just means the system can't pull a value out of thin air. The answer they agree on has to be one that was actually suggested by one of the computers in the first place. And finally, termination. This is crucial. It means the group will eventually make a decision. It can't just get stuck in a loop, arguing forever.
Okay, so we've got a formal definition down, but why does this matter so much? Why have brilliant engineers spent decades working on these algorithms? Well, it turns out the stakes are just incredibly high in our digital world.
I mean, think about it. When the main server in a group fails, the others need to agree on a new leader, and they need to do it fast. When you upload a photo to the cloud, you need every single copy of that photo in every data center around the world to be perfectly identical. And when it comes to money, oh yeah, every computer involved in a transaction has to agree, did it succeed or did it fail? Without consensus, you get absolute chaos. Data gets corrupted, systems split apart, and things just break.
So how do we actually pull this off? Well, over the years, a few major algorithms have emerged, but 2 really stand out. You can think of them as 2 different blueprints for getting everyone to agree on a single truth. Let's talk about Paxos and Raft.
Now, Paxos is the OG. It's the original, it's battle-tested, and it is famously, notoriously difficult to understand, let alone implement correctly. It's just really complex. And because of that, an alternative called Raft was created. Raft had one main goal from the very beginning: be understandable. It simplifies things a ton by making everything revolve around a single elected leader. And for that reason, we're going to focus on Raft for the rest of this explainer, because it gives us a really clear window into how all this stuff works.
All right, let's get into the guts of Raft. The single most important thing that happens in a Raft system is the leader election. Everything else flows from this. It's this really elegant democratic process that just happens automatically.
Okay, so here's how it works. It all starts with a timeout. Every follower node has a little timer. If it doesn't hear from the current leader for a certain amount of time, it just assumes the leader is down. So it switches into candidacy mode. It basically raises its hand, says, I want to be the new leader, and asks everyone else for their vote in a brand new election term. If it gets a vote from a majority of the other nodes, it wins. And just like that, it becomes the new leader and starts sending out its own little I'm in charge heartbeat messages to everyone else.
Now this is really where Raft's genius shines through. This selection process isn't just for getting things started. It's actually the system's built-in immune response. It's how the network automatically heals itself when things go wrong. This is it, the moment of truth for any of these systems. The leader, the one coordinating everything, just vanishes. It crashes right in the middle of doing something important. Is that it? Does the whole system just grind to a halt?
Nope, not a chance. And this timeline shows you exactly how the system recovers. So first, the crash. Leader S1 goes offline. The followers, S2 and S3, they notice pretty quick because those heartbeat messages stop coming. A timeout happens. And because their timers are randomized, S2's timer just happens to expire first. That's the trigger. S2 immediately kicks off a new election for what we'll call election term 2. It asks for votes, S3 gives its vote to S2, and boom, a new leader is elected. S2 now has the majority, it takes over, and the whole system is back online. It all happens in a flash, completely automatically.
Okay, but this is a really good question, because this sounds like it could cause some serious problems. What if the old leader, S1, suddenly fixes itself and comes back online thinking it's still the boss? Do you suddenly have two leaders trying to call the shots?
And here is the truly elegant part of the whole system. When S1 comes back, the first thing it does is talk to the other nodes. It immediately sees that they're all operating in Term 2 while it's still stuck back in the old, obsolete Term 1. The rules of the algorithm force S1 to realize it's out of date. It has no choice but to step down and become a regular old follower of the new leader, S2. Conflict totally avoided. It's beautiful.
So as we start to wrap this up, let's just zoom out from all the technical details for a second. What is all this stuff? The ice cream, the elections, the zombie leaders. What does it all really mean for us?
Well, every single time you use a digital service that you count on, you're benefiting from a consensus algorithm working perfectly in the background. It is the unseen bedrock that lets all these distributed, imperfect computers act like a single, coherent, and trustworthy system. It is, quite literally, how we build trust into our digital world.
And that really leaves us with a final thought to chew on. We've figured out how to make machines agree on simple facts. But as our world gets more and more complex, more automated, this challenge of engineering actual mathematical trust between machines is only going to get bigger and more important. So, what's next?